In this video, we will discuss working with table designs using SQL Server and SSMS. We've already done quite a bit with tables, but we will drill down into some of the details. If you haven't already configured SSMS, you should make this change to the options now. If you don't do this, then when you make design changes to a table that affect other tables or may affect the data in the table, it will refuse to save the changes for you and you will get frustrated. In SSMS, go to Tools, then Options, scroll down to Designers in the left-hand pane, select Table and Database Designers. On the right, under Table Options, uncheck the option that says Prevent Saving Changes that require table recreation. By default, this is checked because if you are in a production environment, it could be an unmitigated disaster if you try to save changes to a table design that require the table to be dropped and recreated. Therefore, this is checked when SSMS installs, and you have to uncheck it. Since we are in a sandbox environment, we don't really care about affecting other users or potentially causing data corruption in our system. Therefore, we can uncheck this box and not think twice about it. Above that option is another option that says Warn about tables affected. That means if you try to save a design change in a table, it will bring up a dialog and tell you that, hey, you're not just affecting this particular table, but you're affecting other tables as well. And you can click through that dialog to continue. I leave that checked because I like to know, I like to get that reminder if something is affecting other tables. On the following slide, you'll see the warning that I was just referring to. If I try to save changes to a particular table, it may affect as many as one or more other tables, and this is the warning that you get. If this annoys you, if you'd rather not see it, you can turn it off in the options, or you can click through it like I do. Let's talk about foreign keys. We've used foreign keys like crazy. We join tables together all the time, but let's talk about how to create a foreign key and look at why we need foreign keys. I'm proposing a real-world scenario. A pizza can have many toppings, and a topping can be on many pizzas. This is a many-to-many relationship because both sides of the relationship can have many connections to the opposing side. There are also one-to-many relationships, and we can also say there are many-to-one relationships, but one-to-many and many-to-one are actually the same thing, just written different ways. There are also one-to-one relationships. Many-to-many relationships, just like many-to-one and one-to-many, are very popular, are very prevalent in the real world. I'm sure if you stopped for a minute and thought about it, you can think of many things in the real world that relate to many other things in the real world in many-to-many relationships. When you're standing in line at Chipotle waiting to order a burrito, think about the many-to-many relationships required to implement a database at Chipotle. I know if I'm standing behind you in line, I may be asking you questions about many-to-many relationships and how they relate to Mexican food and burritos. The way we implement a many-to-many relationship is with what we call an intermediate table. There are also other names for this table, but I will refer to it as an intermediate table. The intermediate table will contain foreign keys into both of the other tables. My naming convention is to use a lowercase t as a prefix, and then use one of the table names followed by an underscore followed by the other table name. It doesn't matter what order the table names come in, since it's many to many, it's a symmetrical relationship from that perspective. So when you see that kind of table in my schema, you know that's an intermediate table. I don't use the underscore for anything else. When you get into the real world, again, you'll be working in places with completely different naming conventions or no naming conventions, and you will be required to adapt. So don't get the impression that this is the only way to do things. Don't get the impression that this is the only right way to do things. This is just the way we will do things. The naming conventions, of course, are documented on Blackboard under the course documents folder. If you haven't studied that, I encourage you to do so now, because I name my tables and my fields in a consistent manner, and if you understand the way I name my tables and my fields, you'll have a much easier time deciphering what I'm doing. Before we jump into the details of a correct many-to-many relationship, let's look at the wrong way that we might implement this relationship. I have SSMS loaded. If you're following along, I encourage you to stop the video, log into SSMS using your personal credentials provided to you on Blackboard. Those will not be repeated here for security reasons. I've created a very simple table called pizza. It has a primary key called pizza ID, which, as you know from our naming conventions, is a surrogate key managed by the database engine and an integer type. And then it has a natural key called pizza, which could be anything. Could be the name of the pizza or who ordered it or whatever. It doesn't matter. As long as I have a natural key and I have my surrogate key, I'm fine. But I also have a toppings table. The toppings table lists the different kinds of toppings that you might have: bacon, mushrooms, tomatoes, green olives. But it doesn't have any direct connection to the pizza table. How do I put toppings on a pizza? How do I tell a particular pizza what toppings that it has? Just skipping ahead for a moment, the solution is the intermediate table, but let me show you the wrong way to do this. If we realize we need toppings, we could add a topping ID field here, and we could say to ourselves that's a foreign key into the topping table. Now I have the capability of putting one topping on this particular pizza. Well, I realized pretty quickly that people don't order pizzas with just one topping. And I'm left with, well, I'm going to solve my problem by adding multiple foreign keys to my table design. And I could continue on and on and on. And what if the restaurant for whom I was designing this database had a limit of 5 toppings per pizza? I could go all the way to 5, topping 1, 2, 3, 4. And it kind of works, but it's a complete disaster when we're joining tables together, when we're writing views. It's also a complete disaster when the pizza restaurant gets bought out by Pizza Hut and they need to go to 6 toppings per pizza or 7 or 8 because I've collapsed, I've destroyed my database design. This is not a good solution. If it's a many-to-many relationship, we need an intermediate table. We don't need multiple columns with the same information in them. Hopefully you realize by now that this is a normalization violation. This is a 1NF violation, and we can't operate this way. This also looks like a spreadsheet, And in the world of spreadsheets, there's nothing wrong with this. But in the world of databases, it's very, very bad. I'm going to throw this away. And it didn't get thrown away, it got saved. That's better. The best way, or the only way, to implement this relationship in a many-to-many construct and to maintain normalization and to be sane about it is to create this intermediate table. The intermediate table will have a foreign key pointing to each of the tables participating in the many-to-many relationship. And there they are. Because we're consistent in our naming conventions, we know that pizza ID is a foreign key into the pizza table, and we know that topping ID is a foreign key into the topping table. We know that because they end in ID and they do not have the same name as the table they are in. We know that pizza underscore topping ID is the surrogate key, also the primary key, because it has the same name as the table and it ends in ID. So again, the benefits of consistent naming, and I will tell you, once you get into the real world, you will not be this fortunate. Things will not be named this consistently, and I encourage you to go ask someone with schema knowledge if you're not sure. Don't spend hours and days trying to decipher a schema where the columns are poorly named. Ask people for help. Again, according to our naming conventions, these look like foreign keys. However, SQL Server doesn't know our naming convention. SQL Server needs us to communicate that in a different way. Therefore, we will go into the table design of this intermediate table and make those into foreign keys. No problem. Right-click on the table, select Design. Notice that it does have a surrogate key, rather. The surrogate key is an identity column managed by the database engine, and the argument could be made that these two columns taken together could also be a key. Okay, but I would call that a natural key because they each refer to things in the real world in the problem domain. So I still prefer to have a surrogate key and a natural key that looks a little weird because it consists of two foreign keys. I'm still not where I want to be though, because I need these foreign keys to be defined to SQL Server, and now they are not. This is what you're going to be doing. Right click, relationship. This is where you define foreign keys. As you can see, there are none in this table. We need to put them in. We need to tell SQL Server that this table contains two foreign keys, one that points to the pizza table, one that points to the topping table. That implements the many-to-many relationship. We select Add. It automatically creates a name for the foreign key. I don't change that. Those are usually named pretty well, and we don't have to go in there and do anything to it. But we do have to define what columns make up this foreign key. We need to provide two columns. Where is the primary key table? In other words, what is the table that contains the pizza? And then what is the foreign key in this intermediate table? Just go from left to right. Pizza. Pick the primary key in that table. Unless otherwise specified, always pick the primary key when you're building this foreign key relationship. And then in the foreign key table, in the intermediate table, pick the matching name. And this looks beautiful, and it helps us sleep at night because the names match. If we follow a convention, we keep it simple, we match the names, it helps us understand what's going on. It doesn't help SQL Server very much. We still have to create this relationship, but it helps us. Click OK. Now we have created a key. The foreign key is pizza ID, and that points to a matching pizza ID, which is the natural key in the pizza table. That's half of the battle. We need to add another foreign key. Select columns and tables. The primary key for this combination will be in the topping table. And that's the primary key in the topping table. And then over here in the intermediate table, we pick topping ID again. So we have topping ID as a primary key in the topping table and topping ID as a foreign key in the intermediate table. Click OK. We haven't saved it yet. Click Close. Try to save it. We get that warning we saw earlier because we are not just causing a change to the intermediate table, we're also creating a reference to the foreign keys in the pizza and topping tables as well. That's what we want to happen, so I'm going to click Yes. And we're done. As an aside, if there had been data in these tables, then you may have had a problem. Because the foreign keys in the pizza table, the foreign keys in the topping table may not have matched up with primary keys in the pizza table. But since there was no data in these tables, we were able to save those changes. So be aware, if you're doing this to production data and there's already data in the tables, it may not be that easy. In that brief pause, through the magic of editing, I have added some rows to pizza and to topping. Let's look at those rows right now. And remember, this slide now is going to look different if you look at it in SSMS, because these two foreign keys now are identified to SSMS as foreign keys. And that shows up right here. So there's the first one that I just did for you. It shows up as FK foreign key. And there's the second one that I just did for you. It shows up as FK foreign key. So the intermediate table now has a foreign key into the pizza table and a foreign key into the topping table. And we have officially implemented a many-to-many relationship using an intermediate table. Here's the data that I snuck in. I added 4 toppings: bacon, green olives, mushrooms, and pineapples. Note the topping IDs. They're numeric. They may be different when you do this on your own, but they're just numeric values generated by the database engine. So the specific numbers don't mean anything. It's just that the fact that they're unique. Same thing down here. I added 3 pizzas. The pizza ID, remember, is just that unique identifier generated by the database engine as a surrogate key. Doesn't matter what those numbers are as long as they're unique, and they always will be. Here's the beauty of the intermediate table. Here is why we do what we do. We want to create a pizza that has bacon. We're going to go look in the pizza ID table for a 12-inch traditional. We're going to go look in the topping ID table for bacon. Then we're going to create a row in the intermediate table that links pizza ID 1, which is 12-inch traditional, with topping ID 3, which is bacon, and that builds the first step in that relationship between those two tables. Now a pizza has a particular topping. So let's do that. And just to make sure the numbers are correct, let's verify what's in the pizza table. 12-inch traditional is pizza ID 1. The unique identifier for that kind of pizza is a 1. In the topping table, bacon is topping ID 3. Our job then is to go into the intermediate table and add pizza ID 1, topping ID 3. Now we have forever created a pizza that is a 12-inch traditional with bacon. If we want to put another topping on that pizza, if we want to put pineapple on that pizza, I don't know why we would, but we could. Pineapple is topping ID 2. We go back to our table again, the same pizza, ID 1, topping ID 2. Now that pizza has 2 toppings. We can reuse the toppings on other pizzas because we have a many-to-many relationship through the intermediate table. And this is something you will do over and over and over in databases that you design. The intermediate table is a very important tool to us, and we need to know how to use it. Let's add another row to this and then write a view based on these 3 tables. Let's say that we want a 14-inch hand-tossed, which is pizza ID 2. That 14-inch hand-tossed should have green olives, which is topping ID 4. Pizza ID 2, topping ID 4. Our intermediate table now contains 3 rows. 2 of the rows relate to a 12-inch traditional, and the other row relates to, I forgot already, a 14-inch hand-tossed. As you look at this, remember this design is not very good because we can only have a few kinds of pizza. We don't have any customers. We don't have a date, a price, anything else that's necessary in the real world. This is simply to illustrate the concept of a many-to-many relationship. This is not intended to be a solution to any kind of real-world problem. Let's close all our tables. And let's say we want to know what pizzas have what toppings. We can write a view that uses those 3 tables. Select pizza as pizza, topping as topping, from T pizza, inner join T pizza topping on P dot pizza ID equals PT dot pizza ID, inner join T topping on T dot topping ID equals PT dot topping ID, order by pizza, and then topping. The inner joins link 3 tables together. We link pizza, we link pizza topping, and we link topping. When we run it, we get 2 rows for the 12-inch traditional because it has bacon and pineapple. It has 2 toppings. We get 1 row in the result set for 14-inch hand toss because it has 1 topping. So this is the benefit, the reward of using that intermediate table to create a many-to-many relationship. Hopefully, at this point in your development, you can write this by hand to join these tables together. We have a view designer. Let's use the view designer to do the exact same thing. Create a new view. I don't know why I got that. Let's hope this works. And let us drag pizza table over here. Let us drag the topping table over here. And watch what happens when I bring in the intermediate table. This is a little bit of magic. Get ready. Look at that. SQL Server told SSMS that those tables have relationships. Because we defined the foreign keys, it added the connections between those tables. You can see that pizza ID in the pizza table is related to pizza ID in the intermediate table. Topping ID in the intermediate table is related to topping ID in the topping table. And look at the code that we wrote. You should see something that looks very familiar to you. We wrote two inner joins just like we did when we composed the query manually in the query window. What we haven't done yet is select the output of our query. I want pizza and I want topping. Now look at this, it's becoming even more familiar. The last thing I want to do then is put my sort order in. I want to sort by pizza and I want to sort by topping. The default is ascending, that's good. And I have a remarkably similar piece of SQL that I had when I wrote it by hand. I can run this. And there's my result set, which is identical. The View Designer then gives us another tool to build or link or join tables together to create useful sets of results. You will quickly outgrow the View Designer. There are many things you cannot do, but you can do something this simple as we did in the query window. Therefore, you should understand how to use the View Designer, you should be comfortable with it, you should be skilled with it, but you should not abandon your ability to write these things by hand, because eventually you will be writing them by hand. Another benefit of a view is that I can save it by name. I can click the Save button, and we use V as a prefix for views. We give the view a descriptive name. We click OK. We ignore this message. It's not a problem. And we look in the View folder. There's the view that we just wrote. Now if I close this little query window tab, sorry, oh there it goes. I can run the view from here. Select top 1000 rows just like I do with tables. And you'll notice that it writes a select statement, but instead of selecting from a table, it selects from the view. We see then that a view is very similar to a table in that regard. I can also go back and change the view. I can go to Design. I can wait patiently. There's my designer again. Exactly the way I left it before. I can wiggle these around. I could add more tables if necessary. But that is an advantage of creating a view. It can be stored as an object in the SQL Server database. This, I'm sorry, the thing that I wrote by hand, which is now gone, cannot be saved as an object in the SQL Server database simply by clicking the Save button. It saves a file to the disk, which does not travel with a database. Learn how to use the View Designer, but be aware you will outgrow it in a short order. Moving on, I want to give you all of the hard work that I have just accomplished, except for the view. I'm going to create a script that gives you the tables, the foreign keys, the indexes, and the contents of the tables as well, the data in the tables. And it's easy to do. You'll notice I'm going to right-click on the database, Tasks, Generate Scripts, Next, and I am going to select particular database objects, even though they're pretty much all that I want. And by selecting those database objects, I can, in a couple of clicks, I can tell the scripting tool that I want the data in those tables, and I also want the foreign keys and neat things like that. Notice I'm not going to select the views. That's my option. On the next window, here's where you have to stop and think, because if you just click Next and you click through this window, you will not get your data. You have to click on Advanced. I open this up a little bit, and somewhere in here, Type of Data to Script, Schema, and Data. Remember, the schema means the tables and the constraints associated with those tables. If you don't select schema and data, you will just get the table structures, you won't get the data. Click OK. Or if you're not sure, script foreign keys defaults to yes. All right? You don't have to select foreign keys, you get those automatically. Where do you want it to go? Well, it'd be nice to have it in a query window, then I can manipulate it a little bit. Or you can save it to the clipboard, and then you can paste it into some other document manager like Word or Notepad. As you do this, keep in mind this is a great tool for small databases. This is a ridiculous tool for anything of any size. You would not back up the eBay schema like this. You would not back up an Amazon schema like this. If you have a small company, a limited number of tables, this is a good tool. If you want to transmit one table, this is a good tool. But for an entire database of any size at all, this strategy collapses very quickly. I selected Save to Clipboard. Actually, I'm going to select Save to Query Window. Click Next. This is a review of all the things you selected. Click Next. This takes a moment. It queries the database. It builds, creates scripts for the tables. It builds insert statements to insert the data into the tables. And since we selected Query to Database window, it builds a beautiful SQL script. And the use of this is twofold. Certainly we can use this to send this schema and this data to someone else simply by transmitting this file to them. It's in human readable form. It also is a tremendous tool for learning SQL, DDL, and action queries as well. Here's a DDL statement that creates a table. So you can look at that and you can learn the syntax of how a table is created. And then you can see how dynamic SQL statements are written. Here are a whole bunch of insert statements to add rows to the pizza table. And here are insert statements to add rows to the intermediate table, and then rows to add to the topping table. A lot going on here, a lot of useful learning opportunities. What I did is I hit Control A to select the entire script, then I hit Copy, and then I pasted that into a slide. And you can't read it, but you can run it. So you can Control A, copy, and you can paste that into SSMS in a query window. All you have to do is edit the first line to reference your database instead of mine, and you can create the 3 tables, and you can create the data in the tables that I did in this demonstration. And I encourage you to do that, and I encourage you to work with those tables. Here's another scenario with a different kind of relationship. This is not many to many. Let me emphasize again, these are not real-world scenarios. We know that a computer can have multiple video cards, but I'm forcing a scenario to illustrate a one-to-many relationship. This one says, a person's computer can have one type of video card, and a type of video card can be in multiple people's computers. This is completely contrived. I know it doesn't work in the real world, but we can say that it is a one-to-many relationship. One computer has one video card. One video card has many, or can appear in many different computers. We don't need a foreign key in a one-to-many relationship. If you're looking for rules to follow, if you're the kind of person that likes rules, here's a rule. In a one-to-many relationship, you don't need an intermediate table. If that's the case, then, if there's no intermediate table, where does the foreign key go? We only have two tables. We have a computer table. Each person has a computer. Each row in the table is one person's computer. We have a video card table. Each row in the table is a kind of video card. Where does the foreign key go? Well, we're building tension by not answering the question. And let's relieve the tension. Here's your rule. The foreign key goes into the one side of the relationship. In this case, that is the sentence that says a computer has one video card. So look for the way that the scenario was written and look for the one side of the relationship. That's where the foreign key goes. And I will leave it up to you as an exercise to implement these two tables. Implement the foreign key in the computer table. Define the foreign key as a relationship using SSMS. And populate the two tables appropriately. If you would like to do that and send me a screenshot, I will give you extra credit.